Hi, everyone. The main idea of our project is that summer rainfall in the southeastern US is crucial for regional water system and farming, and we want to reduce the uncertainties in future rainfall predictions. We used CMIP climate models as they get updated regularly, combined with emerging constraints to make these predictions more reliable. The key to emerging constraints is to refine the probability distribution of future rainfall to a conditional probability function. Projection uncertainty gives us room for improvement. The graphs on the bottom left shows how different the historical and future predictions can be within a single model and across models. The spread within a single model is only 10% of the intermodal spread, which means the latter is the main source of projection uncertainties. The bar chart at the top center shows the variety of historical and future predictions across different models on the x-axis. Now let's talk about metrics. The first metric we use is the mean summer precipitation. Overall, CMIP 6 projects less summer rainfall in the future. After refining our methods, we reduced the uncertainty by 10%. We also compare the projected maximum rainfall volumes and their spatial distribution, as shown in result 3.
Firstly, we plotted a time series figure to show the variation in maximum hourly precipitation during the summer months in southeastern US. Here we use a new variable, PRH max in model FGOS-G3. It is defined as the maximum of the precipitation rate averaged over a whole hour. We chose the maximum PRH max in summer as a proxy for extreme situations for each year from 1990 to 2100. We can see two dashed lines in the figure, blue and red. They represent historical and future projected average PRH max respectively. And with higher level in next few decades, more extreme precipitation can be expected. And this result should be considered when improving the accuracy of the future rainfall predictions in this region.
We also analyze the spatial variability of precipitation. These maps illustrate the spatial variance of rainfall across different regions of the southeastern US. The map on the left highlights that coastal regions experience more variation in precipitation, while inland areas have more consistent rainfall patterns. This distinction is crucial for understanding localized climate impacts. The figures below compare historical and future rainfall variance across different regions using a US-based climate model. By analyzing results from different climate models produced by various countries, we can achieve a more comprehensive understanding of regional climate variability. This comparative approach enhances our ability to predict future climate patterns and devise more effective adaptation strategies.
All in all, our ultimate goal was to refine the accuracy of rainfall predictions in the Southeast United States, and we did this through the analysis of 26 different global climate models, which spanned over 2 decades. And our main methodology was harnessing emergent constraints to enhance the future climate scenarios and to address challenges posed by climate uncertainties. And in conclusion, we found that over 60% of the models analyzed a projected decrease in summer precipitation, which highlights potentially drier summers. Importantly, though, the application of emergent constraints has refined our projections. By establishing the dependency between historical and future rainfall patterns, we have successfully reduced the uncertainty of these predictions by about 10%, indicating a future that may be 25% less dry than previously estimated. The results demonstrate the importance of continuously improving climate models to better forecast and adapt to Earth systems. And as we move forward, it is important that our methodologies continue to evolve, providing policymakers and stakeholders with the tools needed to effectively mitigate and adapt to the adverse effects of climate change.
Okay.